So yesterday we looked at the line of best fit by I. Now, line of best fit by I is easy, as you can see, provided you follow one major criteria, which is what? Actually about two, yes?
It has to cross the main point.
It has to go through the main point and also
Equal number of points on either side of the line.
you must make sure you have almost equal number of points on either side after it goes through the point. Can everybody hear that?
Yes.
Because we only have one period together, so that's why I'm in a hurry. I don't really have time for jokes. Tomorrow when we have double lesson, then we can do whatever we like. Anyways, so that's what we did yesterday. But what I failed to mention, probably because I just went straight to the worksheet, is the concept of interpolation and extrapolation. Interpolation is when you predict within the observed value. What do I mean by observed value? If you look at this information right now, this data talks about the age of the athlete and the distance thrown. Maybe it's javelin or whatever, but the distance they can throw. You can see that the age of athlete is within what range to what range? What is the minimum to maximum? From what to what? 10 to 20. Let's remember that. What about the distance thrown? 15 to 50. Okay. Well, I'm not checking that, so I hope you are right. Oopsie. Now, if you draw your scatter diagram, you put your scatter plots, and you are able to get your line of best fit by I to be this. Remember, you said this is from 10 to 20, right? Okay, let's stop here. 10 to 20. And you said this is from what again? 15 to 50. This is what you have. Okay? If the question is, Rita is an athlete. Her age is 17, for example. Okay? We want to predict the distance that Rita can throw. You could see clearly that we can predict that here, isn't it? Yes?
Yes.
Similarly, by what we know, a line can be extended. Okay? A line can be extended. Which means, if we have some grannies, we all know that we have discussed the idea of causal relationship. Okay, let's say an older athlete, don't go into granny now. Someone who is age 39, I'm sure they still have the muscle, throw something. We are able to also predict the distance. Is that not? But the distance, can you tell me which will be more reliable? The age 17 prediction or the age 39 prediction? Why did you say that?
Because it's within the range.
It's within the range. That is called interpolation. Interpolation is when you are predicting within the observed value. Am I making sense? That line has taken into consideration every data within that group. But the line never took into consideration data outside the group. So while you can predict, it may not be as reliable as the one within. Okay? Of course, if you have no other choice, you can use that to predict. But you want the person you are giving the result to. This is an extrapolation. I'm not so confident in it. But at least in the absence of nothing, I can give you this to work with. Someone who is of age 39 is likely to throw up to this distance. But I'm not so sure about that because my data didn't get to that range. We call that extrapolation. In, within, X, outside. It's as simple as that. I forgot to mention those two terminologies yesterday, so I thought I'd start with that today. So here, interpolating and extrapolating. If we predict y for an x value in between the poles is the boundary here. Okay? The lower pole, the upper pole. The first one and the last one. Do you understand? If you predict in between the poles, then you are interpolating. So we call that process interpolation. Okay? But if you predict outside the pole, then you are extrapolating. So the process is extrapolation. So extrapolation is when we predict outside the observed value. Does that make sense? You can get a difference between when I use the word extrapolation and extrapolating. Extrapolating is like running. Okay? You know, you can say running, going, something like that. That's the same grammatical structure. You get what I mean? Okay? So that's just those two things I need us to know. The accuracy of interpolation depends on how blah blah blah. No. I think I've mentioned that. You don't need to worry too. So again, don't forget, we have your pole. Your pole tells you about the within and outside. So that would be my first short note to write for you today. Okay, I'll just summarize what I've just said, but I thought I mentioned that first. The next thing we want to do today, which of course we will continue tomorrow, is now finding the regression line. The reason we are doing the regression line, we call it the least square regression line, is that the line of best fit is subjective by I. What do I mean by that? Anyone? When you say something is subjective, what does it mean?
It's not fully set.
It's not fully set. It depends on what?
It depends on the person's
It depends on the person. It depends on your feeling. You might be angry that morning and you draw a line. You might be happy the following morning and you are very careful. You draw a better line. What you see as the middle, you know, we always try to make sure, oh, it's in between, right? It's going to pass through the midpoint, the mean point, and after the midpoint, oh, Mr. Daniel said it has to be evenly distributed. Your evenly distributed is different from my evenly distributed. So it is subjective. So how can we now get a more accurate model? That is when we use the idea of the least square regression line. And that's what we want to do today and tomorrow. Because there are two of them. Regression line of y against x and regression line of x against y. Why do we have different ones? You will get to know more about that tomorrow. But today we just focus on y against x. The formula will be proved just for explanation purpose of the class. You are supposed to use your calculator and we will learn how to use that. Hopefully we are fast enough. We use our calculator to do that and you just have to write the coefficients a and b. That's all. So you don't need to worry about what I'm going to prove. But I just want to prove it so that, again, we are used to how proofs are written in mathematics and how you reason in mathematical proofs. That's the only reason I'm going to prove it for you. Understand? So, let's start by writing a short summary of the interpolation and extrapolation. Is this our board?
Yes.
I don't think this is the normal board.
I think this is
The normal board is
Oh yeah, it's this guy. Yeah. It's alright. This is fine. Okay, so let's begin now. Today is 5th, right?
Yes. So line of best fit is from yesterday. Okay, so I'm just going to go straight to it.
I like to tell you how to use your calculator to do line of best fit. Okay, please remind me if I don't have time tomorrow, today, to show you tomorrow. I thought I did the last time. Okay, and one more thing, please, on behalf of the Form 6, I have a request. I will appreciate if some of you could lend also your calculator. I think about 10 should be enough, if all of them want. If you don't mind lending us your calculator, your graphic display calculator like this one, the white color one, yeah, something like that. Please see me after the class. We just need to they have this type, so we don't want this library. So you lend it. So if anyone you have this, Alex, can you ring that up? This type of calculator. Please, I don't mind if you help out the Form 6 for tomorrow's exam. We just put a mark to show that it's yours, or maybe you write your name somewhere, you can identify it. Aha, that's fine. So that they can use it tomorrow for the exam. I have one, but I think 2 or 3 people are already requesting, and I think more people will request. Structure diagram, we could draw a line that best fits the data. Okay. To do this, we must show that the line passes through the main point x bar, y bar of the data, and to all other points are evenly distributed. If they are not on the line, because some of them will fall on the line. So let's just cut off like this. Of course, you don't draw the line before the points. Point, it's going to look like that, and every other point will be down the line or as evenly distributed as possible. So you might have 3. That's going to make it look so even. Okay, let's identify poles. This will be the lower pole of the data. Because it's the first within that range. And this will be the upper pole of the data. Because it's like the biggest in the range. Okay. Respectively, the lowest and highest values. Now, Impose. It's called interpolation. Interpolation. And it is more reliable. Good. Can I call it prediction or estimation? We are not predicting, we are actually estimating, right? Do you get my point? Predict is when you're just guessing, right? So I don't think. No. I'm not talking about in that context. You can't even call extrapolation a prediction because you're already estimating. The prediction is you don't have anything to work with, you're only guessing. When I say Elsin predicted grade is a 7 in IB, I don't have any, I'm just guessing based on what I noticed. But this is not a prediction, this is an estimation because you're estimating from the line. That's what I mean. Any estimates or estimation. Okay, I think that's a better word. Do you guys agree with me on that? Okay, it's an estimation, but I don't think we should call it. Well, it could be. I don't know, whatever. It is more reliable. If the estimation is outside the pool, or in some textbook, it could be called outside the observed values. And that was what my lecturer used in the early 2010. Outside the observed value. Observed means the value we see. Do you understand? Outside the observed value. We call this an extrapolation. So it's not as reliable as the first one. So this summarizes everything. Yes, sir.
What if it's negatively, what's a negative correlation? Then with the output pool and lower pool chain.
That's a
If
good
it's
point
a
there.
negative, yeah.
Yes, because by definition, we're talking about IS value, so it doesn't matter where the IS value is. Do you understand? So do you get this question? This question is, what if it's a negative correlation, which means it's going to come this way? Okay? So a more higher value. Actually, when we talk about the higher value Yanko, we are looking at it from the this axis. Okay? But our prediction is based on here. You substitute x to get y. So your higher x will still be here, even if it's a negative correlation.
So we're looking at the poles with x.
With respect to that x-axis.
Okay.
Okay? Very good question. With respect to the x-axis. So it won't matter whether it's a negative correlation or not. Is there a question over there?
It's with back with the x-axis.
Yeah, that's what we were just saying. Okay. So let's now move to the regression line, which is the main thing for today. Okay? And I'm not going to be needing this guy. Anyone, please? I keep confusing the light with the projector screen. What is wrong with me? Anybody know? Yeah, that's why. I keep going there.
That was the phone for real. I was like on this side.
That's right. I guess I need to tell my brain to start operating in inverse function for me.
This is your small part.
And change. Okay, dude, I'm going to that class, inverse function now. Just change it. If you're operating in degree, please go back to radian. Okay, so let's look at regression line. Regression line. Some call it y on x. The same as saying y against x. Please. I will need full attention here. I will need full attention. I need full attention here. We have about 15 minutes. Okay, so please listen. Because of the fact that this is subjective, like I said earlier in the introduction, we need to find a more precise way to get that accurate model, so that our estimation or prediction, I don't even know, maybe I was right about what I said here, so that that estimation or prediction will be as accurate as possible. Okay, compared to, okay, your model is different from his model, is different from my model, and we are all basing this model on the same data, then it's not right. Just because each of us, we put our feelings, our experience, and all that into it. So we will draw the line a little bit different. Maybe the margin may not be so much, but it doesn't still make it right. So a more better way, that is more of an objective approach, which has nothing to do with anybody's feeling, is this least square approach. Now, how does this work? Let's look at this scatter plot. The y-axis is always the y-axis, x is always x, whether you are dealing with y against x or x against y. Am I making sense?
Yes.
We are interested in finding a line, so which means, of course, the line we have an equation. Okay. Let me just write something like a preamble. Since you may write this, I will tell you where to stop. Since the idea of line of best fits by I is subjective. That is, it depends on individuals. And if I might include my meeting approach. Wasn't paying attention. We need a more precise way of getting the line. Now, let's say this is my line. The equation of the line is y is equal to ax plus b. And this line is said to have described this point. This point. But there might be one on it. Okay. I think this question. Okay. Now, this point has coordinate x1, y1. Let's say this is x2, y2. This is x3, y3. This is x4, y4. And of course, that's the main point, something like that. Please, guys, listen. Please stop right here. We are interested in the accuracy of y is equal to ax plus b. Our focus is not in the fact that we doubt x. That would be the major difference between y and x and y. For the x against y, just to give you x, it will be written in the form of x is equal to maybe my plus n, something like that. We will normally substitute a variable that has been reliably measured. Remember, the other one is an estimate based on this. So your x must be as accurate as possible, because even these are going to be estimated. Am I making sense? in the case of this one, I'll give you some scenario later, definitely in tomorrow's lesson when I discuss this. Your y will be more reliably measured. So it is better to have a format like this, so that with a more reliably data, you can predict x. Rather than have this, where your x is not as reliable as possible, then you are trying to get y from a non-reliable x. Or, if x is reliably measured, and you get the value of y from x, then there's a question asking you to get the value of x from y. You cannot say you make this the subject of formula. Do you get my point? You cannot say you want to make this the subject of formula. No, not in that situation. It's not going to be as accurate as possible. So rather, we need to find something called the regression line of x on y. I'll give you more details tomorrow, because we're going to have a double lesson together tomorrow. But today, we're just going to focus on, okay, x is a reliably measured data. Let us find the corresponding y. That's what this is about. Because we are focusing on finding the corresponding y is likely to have some errors. Because x is very reliable. We don't have any business with any error on x. We focus on y having all the possible errors. Why would y have some possible error? When you were doing your line of best fit, the way you put your intercept is different from the way I put my intercept. So these values will change for each person. So all these are not going to be accurate. So y is definitely not going to be as accurate as we want. So there will be some errors on y. Am I making sense, please?
Yeah.
This is the reason we now say, okay, when is it exactly accurate? When the y we are supposed to get is as close as possible to the point. This line must be as close as possible to the point. That is when it is as accurate as possible. Remember your perfect correlation. What can you say when the correlation coefficient is perfect?
Every point is on
Every point is on the line. In this case, x has no error, even y has no error. Because everything is perfectly fit on the line. But here, x has no error, like we said, this is the reason for this, but y has some errors. Where are the errors? This gap. This gap. This gap in this case. That's a deviation from the line. Am I making sense? Let the deviation for this one be d1. For point 2, let it be d2. Point 3, let it be d3. Point 4, let it be d4. All these d1, d2. In this case, all the d's are what? Zeros. That is why it is perfect. So if the y value on this line is meant to be 4, but the y value on this in this point is 5, there's a deviation of 1. That's what we are saying. If the y value here is 4.3, there's a deviation of 0.3 from the line. Hello?
Yes.
Of course, the deviation here will be -1 because it's deviated. No, actually +1. It's more than it, something like that. Okay. Now, the idea of least square is that we want to minimize this distance, right? But why do we consider least square? The deviation at the top and the bottom we have opposite signs. Some will be positive, some will be negative. So if you had them, you might end up getting 0 and say there's no deviation. For example, look at this.
Did you Daniel?
Yes.
No